Welcome to the lecture on error probability in BPSK. As we know, this is a signal space diagram or constellation diagram of BPSK. I have two message points corresponding to symbol 0 and 1. Okay, so I'll be transmitting this point if the symbol is 0, transmitting this point if the symbol is 1. Now it can be such that I have transmitted 0, but the noise in the channel is such that the received point falls somewhere here. Okay, somewhere here. Received point falls somewhere here. But as we have discussed in the last lecture, if a point falls here, that is in the region Z1, it will be treated as 1. That is, I have transmitted 0, but the received point is in the region Z1, and then that 0 is decoded as 1. Similarly, this received point, this transmitted point, I have transmitted 1, but because of the noise, I may receive a point somewhere here or here, okay, and will be decoded as 0. I transmitted 1, but will be decoded as 0. So these are the errors that can happen in BPSK. If say I transmitted 1 and my received point is in the region Z1, that is from 0, not including 0, 0 to infinity. If I receive a point anywhere here, it will be decoded as 1. Then there will not be any error. And if I transmit minus root TB and receive a point somewhere here in this region, then that will be again decoded as 0, and there will not be any error. But the point, this point, if falls in this region, will generate an error, and then such type of errors we need to find the probability of such type of errors. So the decision rule was this: decide that signal S1 or binary symbol 1 was transmitted if the received point is in Z1, and symbol 0 if the received point is in Z0. So two kinds of error as we have discussed. I transmit 0, but the point falls in Z1 and decoded as symbol 1, and I transmit S1, but received point is in Z0 and will be decoded as 0. Now, what is the probability of making such erroneous decisions? That's we need to find. So let's define Z1 as this. Z1 is a point received between 0 and infinity, and Z0 is a point received between minus infinity and 0. Now what is X1? The received signal point. Just need to correlate with the basis function. Received signal correlated with basis function will give you the received signal point. Now the conditional PDF of the random variable x, given that symbol 0 was transmitted, is defined as this: fx of x given 0, that is symbol 0 was transmitted, then that is this. Okay, we have already discussed this thing in one of the lectures, statistical characterization of correlator output. Okay, so I have transmitted 0. Okay, I have transmitted 0. Then what is the distribution of x? That's what this conditional PDF says. If I am transmitting 0, that is S0 of t, then the expectation of the random variable x is S01. Then you will have a conditional PDF like this. Okay, so what is S01? S01 is root EB that we know. Okay, similarly you can write the conditional PDF of x if I have transmitted 1. Then this will be S1, 1. That is minus root EB here. Okay. Now what is the conditional probability that the receiver decides in favor of symbol 1 given symbol 0 was transmitted? That is, the received signal point x1 falls in the decision region Z1. Okay, I transmitted 0, So this is the conditional PDF of X if I transmit 0. Now, what is the probability that my received signal point X1 will fall in the region Z1? So what is the region Z1? Z1 is 0 to infinity. So to find that, we just need to integrate this conditional probability in that interval. Okay, so this is the conditional probability of X given the symbol 0 was transmitted. Now what I am telling is this: I have transmitted symbol 0. Okay, I have transmitted symbol 0. Okay, I have transmitted symbol 0, that is minus root EB. Okay, but because of some reason the received signal point can be in this region. Now what is the probability that the received signal point is in this region? That will be the probability of erroneous decisions. So this is the PDF. If you integrate that PDF in this region, that will give you the probability that the received signal point is in this region. So what I do is integrate the conditional PDF in region Z1. This is actually the region Z1. Okay, so integrate conditional PDF in the region Z1. Simply integrate that. Now substitute this. Okay, you do a substitution 1 by root n0 x1 plus root tb is equal to z. Then you can simplify it like this. So you just need to change the limits. Okay, so this is p10, and that can be represented by this half complementary error function root ab by n0. So this is nothing but a generalized form of this. Okay, complementary error function. Okay, so okay, or we can say complementary error function. So x to infinity e power minus x square dx. Okay, this is represented as complementary error function of x. So this is it. Okay, this integral is represented by this. So here you have, instead of x we have root eb by n0. So you replace that by root eb by n0. Okay, so half root error function root eb by n0. Okay, now since the signal space is symmetric, you will have p01 is equal to p10. What is p10? I have transmitted symbol 0 but decided in favor of 1. I had transmitted symbol 0 but decided in favor of symbol 1. So that is the probability p10. Now that is equal to half error function of root eb by n0. Similarly, p01, I had transmitted symbol 1 but decided in favor of symbol 0. That will be exactly equal to p10 because the signal space is symmetric. Now the average probability of symbol error is simply average of these two. Since both are equal, average will also be the same value. So probability of error, average simple error in BPSK is equal to half error function of root AB by n0. So this is the equation for average probability of simple error in BPSK. Thank you.